Welcome to Secure Software Development. We'll of course begin this class, as we always do, by talking about Java. Java puts a lot of emphasis on runtime configurability and extensibility, and that includes things like introspection, where a program is allowed to inspect its own code and components, abstraction, and deserialization and serialization of runtime objects. And these are basically the Java way of doing things. And people can sometimes deride this for being very wordy, but it's just the way that things are done in Java. For example, here's a little snippet of a piece of Java code that I dug around and found. So here you have frame, whatever that may be, and we're setting its center property. And we go to the abstract frame property manager. We get the frame property manager. We get the property factory, and then we create a new property from, in this case, some JSON. And we give it the loaded properties, and then we give it a specifier, and that's going to generate, I presume, the correct property for us, and then set that as the frame center property. So a lot going on there, but it gives you a lot of extensibility. It gives you an opportunity to change things at runtime. It's very powerful. And with that, let's talk about the Java naming and directory interface. So this is a common interface to naming and directory services, and there are a lot of them, and you are probably familiar with a few of them. You're probably familiar, for example, with the domain name service, which gives you IP addresses for host names like TennesseeTech.edu. Okay, that's a naming and directory service. There are others, lots of others in fact. And Java has a library that makes it possible to use all of these various things. And like all Java stuff, it's built in layers. And you can see those layers over there on the right-hand side. So what does it look like to use it? Well, one of the things you can do with it is that you can take an object and you can serialize that object out to one of these databases and then later deserialize the object from that database. So what does all that mean? It means if I have an object in memory, a Java object, I can write that object out and store it in one of these services, and then later on I can read that object back in and resume executing that object. That's very powerful. That's pretty neat. And the code looks like what you see over here on the right-hand side. This is taken from an example of using the Java naming directory interface. So you go and import the right stuff. You set things up, and then we're able to go into one of these services and bind a name to a particular object, in this case a fruit object, and then later I'm able to read the object back out of that database. And objects in Java are bytecode, right? So it's a collection of data along with the bytecode procedures that make the object work. Now, let's mention Log4J. A logging framework writes log information. Nothing complicated there. Log4j is an extensible and very flexible logging framework used by a ton of Java projects. And really, you should be using a logging system, right? If you're sitting there and you're messing around with your code and you're adding printlns to your code, or you're adding a lot of print statements to your code to debug it, you're better off using a logging interface and writing debug messages, because you can leave that stuff in. You have to tear it out every time that you solve a problem. You can leave it in, turn on and off debugging, turn on maybe different levels of debugging. It's good stuff. Outputting stuff with like system out println in Java, that's bad practice. You should use a logging framework instead. So let's consider the code over on the right. What's it doing? So in this case, is calculating the value of pi. We give it a number of iterations, and then it performs that sequence of iterations to try to converge toward the value of pi. And you can see we go and get a logger. We then write out the number of iterations. Each time through, we write out the success count. And that lets us later on see what's happening as we try to converge toward the correct result. So, there's plugin support for JNDI. Remember I said there were a lot of different naming directory services out in the world? It would be great if it were possible to add new ones to JNDI. Just add new ones. And you can see here that someone has come along and requested a new feature, has major priority, and it's been fixed. Someone implemented it. Description: currently, lookup plugins don't support JNDI resources. Now, what's happening here? This is from Log4j. Log4j wants to create logging messages, and it wants to be configurable because that's sort of the Java way. And there's this other library, JNDI, that lets you pull information from these named directory services. It would be great if I could configure Log4j from a JNDI resource. Then I could push out my logging configuration through LDAP or some other enterprise-wide database, and everything would just automatically update. And that's what we're talking about here. It would be really convenient to support JNDI resource lookup in the configuration. One use case with JNDI lookup plugin is as follows. I'd like to use the routing appender, whatever that is, to put all the logs from the same web application context in a log file. Okay, great. And I want to use JNDI resources to look up to determine the target route. Okay, you want runtime configuration of Log4j, and you want it to support using JNDI to look up the configuration. Good stuff. This seems like good stuff to me. All right. And at the bottom, you can see there's the patch where this was added to the Log4j library for Java. And there's some discussion. Hi, I've just added a patch to provide built-in JNDI resource lookup with unit tests. Please take a review. Someone comes along and says, your patch was submitted. Please verify and close. Thank you so much, Ralph. I appreciate for the site documentation as well. Cheers. And then this was back in 2013. And then along in 2021, someone comes along and says, nice work, with a little smirky emoji. What's that last part about? That seems kind of odd. Well, let's take a closer look at what this does. So in Log4j, you can log expressions. For example, see that first line over on the right. I could say running with home set to, and then I give it that funny string at the end, which is then interpolated at runtime and filled in with my home environment variables value, so my home address. And so at runtime, that'll come up and that will say, oh, C:/users/ whatever, or it'll say /home/user. It'll fill it with the correct home information. And that's helpful to me in debugging it. Or I could come along and say running with secret key, and I could give you the secret key from the environment. Maybe that's less helpful. Maybe that's a way of leaking information that I shouldn't be leaking. but it's something I can do. And then logging info, searching string, and then I give it this stuff right here. So what is all this? This says go and use the Java name directory interface to connect to an LDAP resource, and here's the specifier for that, and go get that object and use that object to produce a string and substitute that string right here. So the third line down here, we use JNDI to refer to an object in some external server, which is retrieved, loaded into the running VM, and then executes. It's got to execute because we have to compute a string value so we can print it. But think about this. Once the code starts running, it can do anything, and it's running inside your VM now, your Java VM. So maybe that's not a great idea? Well, we can exploit that in a way very similar to SQL injection or JavaScript injection, all those different forms. We can provide a search string to look for, and that gives us remote code execution. Right? If that search string finds its way into a logging statement, it gets interpreted, causing an object to be loaded and executed. That's maybe not good. And that led to what you see here. Apache Log4j is an upgrade to Log4j that provides big improvements, but there's a vulnerability. And you see right here, subject to remote code execution when the attacker controls the configuration. And how serious is this really? Is this really a problem? This requires somebody to enter a crazy string. That string has to make its way to a logging statement in Log4j, and that has to then result in an object being loaded and executed. That seems like a lot going on. Is that really a problem? Yeah, it's a really big problem. It may, at the time I'm writing this, it's widely considered to have been one of, if not the worst vulnerability ever. And lots of stuff became sort of trivially vulnerable. So over on the right you see a screen cap from a video about hacking a computer through Minecraft. So you're in Minecraft, which runs on Java, and in the chat you put in a little string with that little JNDI LDAP trick with your IP address and an object to load. That object gets loaded and executed inside the VM on that machine, and presto, you get control of that machine. Well, maybe you're okay. Maybe it's not that bad. Maybe your code doesn't use Log4j. If your code doesn't use Log4j, you're safe, right? This isn't going to be a problem for you because you don't use Log4j. Except you might. When you look at the use of the Log4j library, about 60% of projects use it but don't specify that they use it because they may not know they use it. What happens is they use a library that in turn uses Log4j, or that uses a library that in turn uses Log4j. It can be as many levels of indirection as you want. But it turns out like 60% of Java projects out there use it indirectly. So they may have seen this and said, well, I'm not affected because I don't use Log4j. But they do. Indirect vulnerabilities are not that uncommon. So if we look here, the blue part of the bar represents direct use of a library, and the orange part indicates indirect use, right? I use something that uses something else that then uses that library. And you can see over on the left-hand side, that indirect use can be small. Over on the right-hand side, indirect use can become quite large. So if you're curious how someone on YouTube would explain the Log4j vulnerability, there you go. There's a video where someone explains it. What if, just pretend, this worst vulnerability of all time had been discovered and reported on back in 2016. Remember, this was discovered in 2021. But what if back in 2016 someone had warned us and said, hey, this is a problem, fix it? That could never have happened. But if it did happen, there'd be a video of someone at Black Hat doing exactly that. You're welcome to watch that. So, what's the point of this discussion? The point is that even code that didn't use Log4j might have used code that uses code that uses code that uses code that does. And you can still be vulnerable. So, how do you defend against this kind of vulnerability in your code? Can you? You're going to use a library. And that library may have no known vulnerabilities, but that library may in turn use another library that does. How do you deal with that? Well, code reuse is what we do. You have to understand that every system is a system built on vulnerable systems because every system is vulnerable. Okay, so it's all totals all the way down. It's all vulnerable totals. Make a reasonable effort to understand the entire software and hardware stack of your design. Okay, and you have to accept that you may not fully understand all of it, but you should make a good faith effort to do it. And there's stuff that will help you do it. There is software that will produce a SBOM, a software bill of materials, and you can integrate that into your build. So for example, when I'm building with Rust, I use Lich King, which checks my libraries, and Cargo Audit, which audits all the libraries I'm using to warn me if there's a vulnerability somewhere in that chain. Now, you may say, well, I'm just not going to use any third-party libraries. Oh, good for you, I guess. You're still going to probably use the operating system libraries, and it's impractical to do that, right? You're not going to reinvent every wheel. So when you realize that you're going to have to use third-party libraries and you have concerns about them, you may want to limit your use to certain specific features. For example, with Log4j, you could have limited your use of features to prevent that stuff from happening, right? And you could have done that by sanitizing the input. Now, a way of doing that, a design pattern oriented way of doing that, is to surround third-party libraries that you use with a facade or an adapter. And there are links there to the correct design patterns for that. This is not a design patterns class, but facades and adapters are both ways for me to bring in a third-party library and strictly control the features of that library that I use to centralize my use to the facade or the adapter, so that if a problem like this does come up, I don't have to go through my entire code base and rip stuff out or change things. I can go to the facade or the adapter and make the changes there. It's not always practical to disable features of components you use, but it is practical to try to understand and document why you're using each component and what features you need. Okay? And then remember the basic line that we've said several times already in this class: don't pass unvalidated information to other components, and validate information that comes to you from other components. Okay? Right? Keep track of the HBOM. It's a hardware bill of materials if that's relevant to your project. Build a software bill of materials for your project. And where possible, it's good to use an automated SBOM utility, as these can also do other things for you, like make sure you're not using incompatible licenses. Okay. Sometimes when you bring in some stuff and run a license check, you may discover that somebody else down the chain is using an incompatible license. It was not obvious to you, and maybe they're in the wrong, but you're still responsible for the code that you're going to produce and ship. Using a facade is a trade-off. The advantage is a single point to manage the security and fixes for an external component, and the ability to just rip out and replace bad software. Okay, this logging framework is bad, but I've centralized my use to this one piece, so I can easily replace that with a different logging framework, and the rest of my code won't have to change. The disadvantage is that, I have to consciously work to expose any capabilities that I want to use. And if I don't do that through my adapter or my facade, I can't use those capabilities. And it adds non-product code that you have to maintain. It adds that code that's an adapter or a facade. If that third-party library changes, that's great. You've got one place to update. But it also means you have to maintain that additional code. Define the structure of information you expect to receive and write code to validate that structure. Right? That's it. That's basically input sanitization. You're going to take something in from a user. You're going to pass it around in the system. Make sure that nowhere along that path is something automatically interpreting it and then executing stuff based on it. Okay? So do all that checking. Take responsibility for the data you pass to other systems and accept responsibility for the data your system is given. All right. So let's talk about why security is different from other properties. So attacks by an attacker, someone who's an adversary attacking your system, are not random. Those attacks are not random. They are systematic. So we're pretty good at designing systems to withstand random bad events, but we're pretty bad at designing systems to withstand systematic attacks or events. So we may say, well, the chances of this happening are small. Well, the attacker is going to make sure it happens a lot, and hopefully to them, break our security. Security is invisible, and it's hard to measure. Right? So is the computer I'm working on right now compromised? There's no light that goes off. So how would I know? Well, I could try scanning it, but is the scanner itself compromised? I don't know. Right? Security is often invisible. It's highly contextual. That's a recurring theme that we'll revisit throughout the entire class. Security depends on context. It's a property of systems. So I may have really good security for one component, and when I combine that with other components, that security guarantee may go away. And that's because the composition problem for security is unsolved. I don't know how to take two secure systems, plug them together in such a way that the resulting system is going to be secure. I don't know how to do that. Security is often binary. Either you're secure or you're not. Right? A little tiny, seemingly insignificant little silly weakness can be leveraged to give you remote code execution, and basically there's no security. It's often an assumed property. You grab something and you're like, well, this is probably secure. Someone somewhere has done due diligence to make sure this is solid stuff. I'm just going to grab it and plug it in. So it's often an assumed property, and security degrades. Yesterday my system was secure, but then someone pushed out an update to Log4j. Now my system isn't just insecure, it's horribly insecure. All systems are systems of systems, of systems, of systems, of systems. We don't know how to compose secure components to yield secure systems. That's the composition problem, and it's unsolved. Go and solve that and make a great name for yourself. We'll all be grateful. An adversary will exploit vulnerability wherever they can find it. So, in the world of programming, once you have a solved problem, the next thing you want to do is then compose that solution with the solutions to unrelated problems that share some of the same resources. That's really what you do. And we can think of that stack as what you see over here on the left. At the very bottom, fundamental physics, right? Electrical fields, light on fiber, so on. Just above that, we have some hardware that you'll need for the particular purpose of your application, and then probably a bunch of hardware that's unrelated to it, right? There may be unused network ports, or cards. There may be a bunch of different ports and components in your machine that you're not using. Above that, you have software that you need to use to get your mission done. Then you have software that's unrelated to your mission but still on the device, right? And then you have software with known vulnerabilities. All those things coexist. There is software with known vulnerabilities on your machine right now. Just guarantee it, right? It takes a while for known vulnerabilities to make their way through, where there's a patch, then to be publicly disclosed, etc. And there's unrelated software, right? You've probably got software on your computer to do tons of things not related to the specific mission you're trying to do. And then on top of that, you have the operating system, other software. You may have software that's segmented off. That's great. Then above that, you have people, some of whom may be malicious. And on top of that, you have policies and procedures of organizations and how those all work. Even if it's your home machine connecting to the internet, you're subject to policies and procedures, for example, of your ISP. It's a lot. And we try to do some good by creating these boundaries. See those red lines there that let us segment the system up? They're not always perfect. You can see that in that blue area of the software, I can go around that red line. I can go from the operating system or from my software down into unrelated software and then back up, and we'll see that kind of vulnerability later on. And that can be a source of a vulnerability. Vulnerabilities occur at the edges. That's typically where two of these things touch. They occur where there's an interface or a protocol. And what you're seeing over here on the left-hand side is basically a view of a single computer. But I might put that in a network of computers. I might connect that network to big motors or inverters or other kinds of industrial equipment. And all those different things create new boundaries and connections, and each of those may have to have a different security posture. And that creates this complex system where, again, vulnerabilities can arise at the edges and move throughout the system. So let's talk about vulnerabilities versus bugs. So it's common to hear people say, well, vulnerabilities are caused by bugs. Something in your code isn't right, and that's where the vulnerability comes from. Well, let's go back and think about Log4j for a minute. You built your application, you understand it, and it's secure. And it uses, let's say, Log4j. Let you directly use it. You limit your use to a few methods, and you trust Log4j, but only a bit. Known or maybe unknown to you, Log4j uses the JNDI. and maybe you don't even know that that's the case. Maybe it didn't use the JNDI when you wrote your code, right? Because that was only introduced later with an update to Log4j. So when you wrote your code, that may not have even been a thing. Okay? Now, the thing to remember is all of this code can be working as designed, working correctly, right? The JNDI stuff, the Log4j stuff, they were doing what they were intended to do. This was an intentional feature added to Log4j. All this code worked correctly. There was no bug. But there was still a vulnerability. Okay? Sometimes you can do everything quote unquote right and still lose, right? What happened here? Within the Log4j world, they wanted to add a feature. Remember we mentioned that adding a feature to a secure system can sometimes make that system insecure. That's what happened here. In addition, they increased the configurability space, but they didn't check for the security of that new space. So they broke a lot of the rules that we've talked about in previous classes. So just to re-emphasize, adding a feature to a secure system can make it insecure. A great example of that is this talk at DEF CON that I'd recommend you watch. Christopher Domas discovered that there was a hardware backdoor in certain versions of the x86 processor. It basically had a second processor in it, and that one didn't really have security, so you could use it to get control of the main processor. It's a fascinating talk. I highly recommend you watch it. So one way you can think about security is to consider security to be a set of guarantees. Okay? And ideally there would be theorems you could prove about a system based on these guarantees. Alright, so let's go ahead and clean up some language. We've been saying vulnerability, weakness. Let's go ahead and try to nail down what those things are. So an exploit, according to Cisco, is a program or piece of code designed to find and take advantage of a security flaw or vulnerability, seems like maybe those are the same thing, in an application or computer system, typically for malicious purposes, such as installing malware. This is a very wordy definition. An exploit is not malware itself, but rather it is a method used by cyber criminals, sure, to deliver malware. Okay, that's a lot going on there. If you'd like to see someone doing this stuff, I've included a video of someone using Metasploit over there on the right. So let's ask some questions here of that definition. Does an exploit have to be code? What about a malicious configuration file? Maybe your system uses a configuration file, and maybe that configuration file is not protected. Maybe it's something I can get access to. Maybe. So let's say, just for the sake of argument, this is a thing that could never happen, I'm sure. Let's say that you use a piece of software. That software has a configuration file stored in your local home area. Could be on Windows, Linux, don't care. That is a file owned by the user. So if I can just get access to that file using your user permissions, I can modify that configuration. And then later, if you use that application to access protected resources, I may be able to have set up the configuration to allow me to have access to those protected resources. That's interesting, right? That could be problematic. Let's say a concrete example of that is SSH and your SSH keys. If I can get access to those, I may be able to leverage those to give myself access to lots of other systems. Okay. So an exploit doesn't necessarily have to be code, I would argue. Let's give another definition. An exploit is a method, could be inputs, could be environment strings, could be combinations of all that results in a system performing an action that violates a security guarantee. I tend to like this definition a little bit better. It's a little more broad, and it includes just other stuff. And I can maybe see how to apply this to hardware systems. So the code you see over on the right hand side has a vulnerability. What is a vulnerability? So according to the CVE, Common Vulnerability Enumeration, a vulnerability is a weakness in the computational logic found in software or hardware components that, when exploited, results in a negative impact to confidentiality, integrity, or availability. And they go on and talk about it. Okay, fine. I guess that's a fine definition. Again, very wordy. What's happening over on the right-hand side? Well, in this code, there is a buffer overflow vulnerability. This is real code. I can't remember where I got this code, but I love this piece of code. It's actually a little example that was used to demonstrate buffer overflows. I think it comes out of, I think this code comes from the CERT secure coding guidelines, I believe. Not positive. So we create a buffer of 15 bytes. We ask for the password, and we just read it straight into the buffer. We compare it to a password, and if it doesn't match, it's incorrect. If it does match, we say it's correct, and we set pass equal to 1. And then later on, if pass is set, we say we're authorized, and we do whatever authorized stuff we need to do. So, but look how things are set up. The buffer has links 15, and that's followed by this integer pass. So if I put in something longer than 15, presumably those extra characters will overwrite pass, right? These are both variables that live on the stack, and in most layouts, one right after the other. And so this would overwrite pass. So I could enter a bad password. It would tell me it's an incorrect password, but I've overwritten pass so that now this works and I am authorized, even though it told me I had an incorrect password. You can take this code and play with it. There are usually protections for some of this in some modern systems, but it'll still work on a lot of them. So I mentioned the CVE, the Common Vulnerability and Exposures, and this is a MITRE developed international standard for identifying vulnerabilities. And it's a really good idea. So instead of trying to describe a vulnerability, give some nebulous, that thing where this happens, you are assigned a vulnerability identifier, and everyone can use that identifier to talk about the same vulnerability. So if you want to know if your company has patched something or how bad it is, you can go and look it up. The Common Vulnerability Scoring System, CVSS, is a way to measure the potential severity of a vulnerability, and it does it in a few different dimensions. Okay, impact, exploitability, just a bunch of different stuff that are combined to give you a score for a particular vulnerability. Okay, and so over on the right hand side, we see the score for a particular vulnerability. In this case, CVE 2021 34523. You can look it up, and we see that that was a 9.8. Very, very, very bad. Don't worry, Log4j scored a perfect 10. You can go visit the National Vulnerability Database at that link and poke around and see what's on there. So the nice thing about the CVE designation is you can look up the vulnerability in public databases and in your supplier databases to see if it's been patched. And that's important. And to see if there's research on it or information about it. It's a great that you have this nice identifier out there in the world. Now, the existence of an exploit implies the existence of a vulnerability. What are you exploiting? You're exploiting the vulnerability. Okay? A thing is not a vulnerability unless there is an exploit for it. Okay? So how do you prevent vulnerabilities in programs? It's kind of the bottom line to a lot of what we want to do in secure software development. Well, we really need something to look for, something we can go and get our arms around and say, this needs to be improved. So a piece of code by itself might not be vulnerable, right? Each line of your code is probably not a vulnerability. But together they can become a vulnerability or become part of a vulnerability. And that could be in some particular context, or that could be in combination with other code or other systems. So let's talk about weaknesses, because vulnerabilities really arise from weaknesses. A weakness is a flaw, fault, bug, or other error in software or hardware, code, design, or architecture that, if left unaddressed, could result in systems, networks, or hardware being vulnerable to attack. This is a pretty good definition. Again, very wordy, but it's a pretty good definition, and it covers a lot of space. Could be hardware weakness, could be software, could be a combination of those, right? Could be the implementation, the code, the design, even just the architecture of a system could have weaknesses. And those could be exploited, and once they're exploited, they become a vulnerability. Okay? It's not one-to-one though. There may be a weakness in a particular library, a weakness in another library, a weakness in the third library, and by combining those three weaknesses, I achieve a vulnerability which then is exploited. MITRE has something called the Common Weakness Enumeration, the CWE. Once we've observed a weakness out in the world, right, we have, let's say, an exploit. And we say, what's the vulnerability? We put that in the CVE. And we say, what are the weaknesses on which this vulnerability depends? We go and identify those, try to assign them to different categories, and put them in the CWE. And that's great. That gives us a list of things to check our code against to see if we have any of those weaknesses. Unfortunately, it's not small. It's very large. There's a lot of CWEs. And people have developed tools that can scan your code for CWEs, but often they produce a lot of false positives. So, we can ask interesting questions, like we could say, what are the most common weaknesses? And in fact, MITRE has a top 25 list. This is the one from 2023. We're still in 2024, so we don't know what that's going to be yet, but we'll know next year what the top for 2024 is. What's at number one? Out of bounds right. And it just goes on from there. You'll see null pointer dereference down there at number 12. Okay, these are the big ones. These account for a lot of the vulnerabilities out there, exploiting one or more of these weaknesses. All right, this was all maybe a little abstract. Let's go look at a concrete example of this. And instead of picking on code, I'm once again going to pick on hardware, because I like picking on that. I want you to get a security mindset that generalizes. Don't just think about code as the source of weaknesses and vulnerabilities. Weaknesses, vulnerabilities, exploits are present everywhere in every system. So here is a view of a door, edge on, and you can see the bolt, which is that big piece of metal over on the left, and you see the Deadlatch plunger, which is that little smaller bolt to the right. And you probably noticed this on some doors, that are meant to be secure. Now, when you close the door, you notice how the bolt has that slope to it. When you close it, the bolt hits the strike plate, and the bolt is pushed in by the strike plate until it reaches the mortise. That's the hole in the wall there, and then the bolt pops into the mortise and the door is secured. But because of that little ridge there, I could perhaps insert a credit card. That's kind of the classical thing to do. To prevent that, a lot of doors have a door jamb that extends out past the door a bit. Fine, that's not a problem for me. I can use something that can go around that and then push on that and get my way in, right? I could use some laminated cardboard. That would work. A thin piece of laminated cardboard works just great. So that would not be secure. So these locks add a Deadlatch plunger. That's that little piece there. What happens is the bolt goes into the mortise, but the Deadlatch plunger does not. It is stopped by the edge of the mortise, and it doesn't go in. So it remains pushed in. And because it is pushed in, the bolt can't be retracted. So think about how this works. Right now the plunger is out, and as the door closes, the bolt is able to be pushed in because the Deadlatch plunger is extended. Once the door closes, the Deadlatch plunger is pushed in, and so now the bolt can't be pushed back. Good, secure system. They show up everywhere, right? Here's one on a different door. In this case, it's not a little plunger. It's this metal piece that, when it's fully extended, you can't then push that little guy back in. So the Deadlatch plunger engages when the bolt itself is fully extended. If the bolt does not fully extend, right, when the bolt falls into the mortise, if it doesn't go all the way in, the plunger can't engage, and that means the bolt can be pushed back in. Well, that's not great. So this is a weakness. Specifically, what is the real weakness here? I close the door. I assume all this system is working correctly, but there is no visual indicator that the Deadlatch plunger has engaged. There's no visual cue that the lock is not in a secure state. Why wouldn't it be? Well, there might be something in the mortise, right? Maybe what I did was, while I visited your office, I shoved some Legos or some gum or something in the mortise of your door, and now when you close your door, the bolt clicks in, but it doesn't go far enough for the Deadlatch plunger to engage, and as a result, I come back later and I just slip a piece of plastic or a credit card in there and open your door and walk in. That's not great. So this weakness can be exploited and become a vulnerability. And specifically, what is the exploit? The exploit is I shove something into the mortise when the door is open, and then later I push the bolt back and walk in. That's the exploit. So it's not unusual for systems to have indicators that a protective measure is engaged. In fact, you should do that, and lots of systems do. And you can see some over there on the right hand side. Some of them are simple, like if you are part of the gun crowd, you probably know there's an empty chamber flag that you can slide into the gun. When that flag is present, you know that it's sticking in the chamber, and you can't have a cartridge in the chamber because that little flag is blocking it. so you know the gun is in a safe state. There can be tons of other ones. They can be complex. The little lock icon on your browser is actually pretty complex, right? It requires that your browser has checked a certificate path back to some root certificate, and decided that the site passes some checks, and then it puts that little lock icon up there. Windows does this. Down in the system tray, you have a little indicator to say, hey, you need to turn this on, or this is not enabled for some reason, and you should fix it. And it'll often have little pop-ups that will warn you if something isn't right. These are positive confirmations of success. So, just because a weakness is widely known doesn't mean someone has fixed that weakness. Weaknesses can persist in systems for a long time, a very long time. And we'll see some in the course of this class that have been in there for a long time. So, remember, all systems are vulnerable. Whenever you can, give a way to verify that a protective measure has been engaged correctly. Okay? Now you have some addition to your system. This feedback. You have to consider, how do I defeat this verification? Is there a way for somebody to modify the lock icon in the browser? If so, that's not great. Okay, let's have a little discussion. This will be a classroom discussion, so there's not much to say here. And the question is it possible to have an unexploitable vulnerability? And if so, how would that work? And we'll talk about that in the class. There's homework. The homework is to pick a system, choose some aspects, define the boundary of your system, state a security property, and explain how a weakness in that aspect can be used to violate a security property. Give an example of a blended attack, and then identify a side channel and describe what information can be inferred from observing the side channel. This is to get you beginning to think about the security of a system. That's it.